Okay, so welcome to another video on vector calculus. In this video, we're going to be talking about surface integrals. So the first thing I wanted to talk about is essentially what a surface integral is, and essentially just define what would we talk about when we talk about a surface of a function. So what we can do is we can start with for general definition of what arc length is. So this is basically something that we have already done in single variable calculus. So you know that if you take a portion of a curve in 2 dimensions or 3 dimensions by that sense, and then you basically just take a portion of the arc length that is so small, infinitesimal small, such that it can be considered a straight line, then you can relate it to the increment in x and y via Pythagoras theorem. And then you know that if you take basically if you write the relation dl squared equals to dx squared plus dy squared, then what you can do is you can divide both sides by dx squared, and then you can rearrange everything to solve for dl, and then you get your element of arc length in terms of the function dx, because this is more convenient if the curve is represented as a function of x like we have here. So then what you can do is you can find the arc length of that curve. So let's say you have two endpoints A and B. You can find the arc length by simply integrating over all those increments of the little arc length element, which is basically just this. Now you can construct a line integral, and this is something that we did basically by taking this integral, but now you're integrating a function of 3 variables, or it could be a function of 2 variables as well, or any variables for that matter. And then you're going to integrate it with respect to that element of arc length. So basically that's going to give you, instead of just the length of the curve, it is going to give you the area of the wall that is constructed between this curve and then whatever surface or hypersurface you're dealing with. Now if we go to a more general case, if we have a function of 2 variables like z equals to f of x and y, then what you can do is you can take a little portion of that surface, an infinitesimal portion of that surface, and you can call that element an infinitesimal element of surface ds. Now, by analogy with the arc length element that we derived in the first equation, we can do the exact same, but here now we have 3 directions, so we have to take into account that we have elevation in x, y, and z. So the derivation turns out to give you the following. So we basically start off in the following manner. We're going to get this element here, and then what we're going to do is we're going to differentiate that surface with respect to x and then with respect to y, square those two, and then you have a 1 here essentially because this element corresponds to the surface differentiate with respect to z, but we know that z is a function of x and y, so obviously this is just going to become 1, which is this element here. Now what you can do is, if you wanted to find the surface area of a particular function within a particular surface, so say that you can find the surface to this particular domain S, then you can find the surface area within that constraint simply by adding all those increments in the surface area element. So just in the same way that you find the arc length of a curve simply by adding up all those little contributions of arc length. Now obviously this notation is going to get a little bit confusing because you have s here, you have s there, so it's just a matter of keeping up with tradition. So this is how most textbooks would have it, and essentially it is a surface, it is not a flat domain like we have here. So by definition, if we extend this by basically putting a function inside of this integrand, then the surface integral is simply this integral with respect to some function of x, y, and z. And you might imagine, well, that seems pretty straightforward. So as if you have a function of z in terms of x and y, then you can pretty much use this kind of substitution. So you know that your dA is just going to be your element of area, which can be in Cartesian coordinates, dA is equal to dy dx, depending on which order you're integrating. In cylindrical coordinates, you can have r dr d theta. So this should be polar coordinates because it's an element of area. and so on and so on. So basically this is going to be an element of area for each of those coordinate systems, and you can have one for spherical coordinates as well, but we'll get to that a little bit later on. So now, in order to show you how this works, what I'm going to do is I'm going to show you how to solve this example. So we're given a function that is solely a function of y here, and we want to evaluate the surface integral with respect to that function. So the surface that we're given is defined by this function of two variables, so z equals to x plus y squared, and we're given the limits on x and y. Now, why do we need limits on x and y? Remember that a double integral needs to have limits because we need to integrate it to get a numerical value. And also because the domain S here, which is what constrains on which area of that surface you're calculating the surface area of that integral, this is basically just a projection of that domain D. So you need to define a domain on the xy plane, and then wherever it cuts the surface, that's going to become the domain of integration S. So now this is the domain we have on the xy plane, and what we're going to do is we already have the limits, so all we need to do is just put everything in there. So the first thing we need to do is to find out what that element ds is. So element ds is going to be dA times the square root of z with respect to x plus z with respect to y plus 1. Alright, so now what we need to do is find out what those derivatives are. So let's differentiate z with respect to x first, that becomes 1. Then we differentiate z with respect to y, and this is going to give us 2y. So now we go down here and we can write the element of integration ds in the following form. We can have dA times the square root of the following, so we have 1, so 1 plus 1, that's 2. And now we have 2y squared, so this is going to become 4y squared. And now we can, we couldn't really take the 2 out, so let's just leave it at that. Now what we're going to do is we're going to plug this into our integral here, and we're just going to integrate it. Now at this point it's probably better to decide, well, which order of integration are we going to do. But first of all, let's write the integrals. So we have double integral of the function y ds. And now what do we have here? Well, it turns out that we're going to have the following: d of y times the square root of 2 plus 4y squared times dA. Now, which should we integrate with respect to y or x first? Well, we notice that it doesn't really matter in this case because both limits are constant. So the limits on x are constant, the limits on y are constant. So if we reverse the order of integration, everything is going to stay the same. So, but in general, I like to start with whatever function we have inside. So let's start off with y on the inside. So that means that we're going to put the limits of x on the outside. So 0, 1 here. Then we're going to have y here. So that's going to go from 0 to 2. And here we're going to have y times 2 plus 4y squared. And then we're going to have dy times dx. Alright, so now for this integration, what we need to do is we're going to have to do some substitutions. So let's say u equals to 2 plus 4y squared, such that du is going to be 8y dy. And now, of course, what we need here is to basically multiply this by 8, because we want this to be 8y, not just y. So let's put an 8 here, and that means that we're going to have to divide by 8 outside, and that's basically to balance it out, because we're basically multiplying this by 8 over 8 so that it becomes 1. So now that we have this, we can replace the integral by this. So we're going to have 1 over 8 from 0 to 1 of the integral from 0 to 2. And now this here times that is going to be du, and then the rest is just going to be u. So we have square root of u du dx, and then this is going to be 1 over 8 of the integral from 0 to 1. Now we integrate this here, so this is going to be u to the power of 3 on 2, so 2 on 3, because we're dividing by 3 on 2. Now u was originally this, so let's write it down, 2 plus 4y squared to the power of 3 on 2. We're gonna integrate this from 0 to 2, and then with respect to x. So now we're going to have the following: 1 over 8, integral from 0 to 1. Okay, so when we put 2 in here, that becomes 4. 4 times 4 is 16, then we have 18. So 2 on 3. Actually, let's take the 2 on 3 outside. Okay, so we're gonna have 2. This is gonna cancel out with the 8, so this becomes 1 on 4 times 3, that's 1 on 12. So now we're gonna put this in here, so we have 16 plus 2, that's 18 to the power of 3 on 2. And then we're gonna put 0, so that's gonna be minus 2 to the power of 3 on 2. And all of this is gonna be integrated with respect to dx. Okay, so now we can probably take this out as well, so we're gonna have, I'm just gonna solve for this a little bit later on. I don't wanna try to think about this. So we're gonna put it outside, and then we're gonna integrate, well, this is just gonna be a constant, so that becomes x, integrated from 0 to 1, and then we're just gonna get 18, 3 on 2, minus 2, 3 on 2, over 12. And now let's see if we can simplify this a little bit further. So at this point, it's just basic arithmetic, so okay, let's do it here. We have 18 times square root of 18 minus 2 times square root of 2 over 12. Let's see, okay, so this is 9 times 2, so we can take the 9 out, so this becomes 3 times 18, that is going to be 54, I believe, times square root of 2 minus 2 square root of 2 over 12. Sorry, it should be 12 there. And now we have 52 times square root of 2 over 12. And what else do we have here? Okay, and we can simplify this to 13 square root of 2 over 3. So that's the answer I was looking for. So basically, this is going to be the value of the surface integral of y with respect to ds along this surface here. So we have our domain on xy, the surface is going to be the projection of that onto the surface here, and that is it. So basically, this is how you would find a surface integral from, by using this kind of definition. So if you have a function, say set explicitly as a function of x and y, then you can use this kind of thing. Now, of course, as it happens in a lot of cases, our surfaces are not always going to be a pretty function like this. So sometimes we're going to have closed surfaces. So let's say we could have a combination of surfaces like this. We could have a cylinder, and then it is cut at some angle here from the horizontal, and then maybe it has something like a hemisphere on the bottom. So obviously in that case, we're going to have to resort to a much more delicate treatment. So in the next video, we're going to have a look at a more general view of surface integrals, which uses oriented surfaces, which uses vectors and vector calculus to do that.